Somewhere on a monitored structure, two sensors are listening. One sits on a footbridge, footsteps constantly. The other sits on a load-bearing beam, and for most of its life, it says nothing at all. Then one moment, it fires, and the ground beneath it barely reacts. Every optimizer you have met so far uses one shared step size for every parameter. Today we find out what happens when that stops being good enough. We have built up from the perceptron, to backprop, to loss, to gradient descent, to momentum, and every one of those methods shares a single learning rate across every parameter in the model. Today's question: what if every parameter could earn its own step size, based on its own history? This is AdaGrad. AdaGrad, giving every parameter its own footing. We will build the update rule term by term, prove with real numbers that no single fixed step size can do both jobs at once, and find the exact point where even AdaGrad's own fix eventually freezes solid. Picture two sensors. Sensor 1 sits on a busy footbridge. It reports a small vibration on nearly every step, all day, every day. Sensor 2 sits on a load-bearing beam that almost never moves. It can go quiet for the entire monitoring window until the one moment it really matters. A real structural stress event. Miss that, and you have missed the only signal that counted. Now imagine training these two readings with a single shared step size. Tune it small, so the busy sensor's constant chatter does not destabilize your model, and the rare event on the beam barely registers, a whisper instead of an alarm. Tune it large enough for that rare event to land properly, and the busy sensor's constant updates now overshoot wildly every single step. One number cannot serve both jobs. That is not a tuning mistake. It is baked into how differently these two signals behave. Here is the fix. Give every parameter its own step size and derive it automatically from that parameter's own history, not the direction it has moved, just how much activity it has already seen. A parameter that has been pushed constantly has earned a smaller step. A parameter that has barely been touched keeps its full step, ready the moment something real finally happens. Think of it as ground that hardens with footfall. A well-trodden path packs down over time. Each new step moves it a little less. Untouched snow stays soft, so the first real step still sinks all the way in. For every parameter theta, we track one running number g, starting at 0. At every step given gradient g, g updates to g plus g squared. Then theta updates to theta minus, the learning rate, divided by the square root of g. Take that root first, then add a tiny epsilon to it, times g. Why square the gradient? Because we want to track activity, not direction. A push forward and a push backward should count the same toward how packed this ground has become. And squaring punishes big jolts more than small ones. A large gradient contributes far more to g than a small one. Why the square root? Because g accumulates in squared units, taking the root brings it back to a real learning rate scale. And epsilon, it is a sliver of resistance, just enough that dividing by g does not break when a parameter has not seen a gradient yet. Once g has any real size, epsilon does almost nothing at all. This is not just a good idea, it is the solution to an actual optimization problem. In 2011, Ducci, Hazan, and Singer showed that this per-parameter scaling falls directly out of minimizing regret against the best fixed choice in hindsight, under gradients that can be adversarial, worst case, not just noisy. It is not a heuristic bolted onto gradient descent, it is the answer the math itself produces. Here is the proof, in real numbers, over 100 steps. Sensor 1 fires every single step, gradient 1. Sensor 2 fires exactly once, at step 100, gradient 3. Tune plain gradient descent with a small step size, small enough to keep sensor 1 stable. Sensor 1 moves a controlled 5 units total, but sensor 2's one critical event moves it only 0.15 of a unit, basically ignored. Tune that same step size larger, big enough for sensor 2's event to register as 3 full units, and now sensor 1, hit by that same size every single step, drifts by 100 units instead. Now watch AdaGrad using that exact same larger step size, no retuning at all. Sensor 1's own accumulated history reins it in automatically. Total drift stays under 20 units, 5 times more stable than plain gradient descent at that setting. Sensor 2, whose history stayed near 0 right up until its one real event, still moves a full unit, smaller than the 3 units big eta gradient descent gave it, but delivered without wrecking Sensor 1 at all. One hyperparameter, both wins, no fixed step size can do that. Let's see this in actual code. 2 arrays hold the running accumulator G, 1 per sensor, both starting at 0, alongside 2 arrays for theta. The training loop is a handful of lines. Take this step's gradient, square it, add it into G, take the square root, add epsilon, divide the learning rate by that to get the effective rate, then multiply by the gradient for the actual update to theta. Run that loop 100 times, once per sensor, printing G, the effective rate, and the update at every step. Look at the printed table and the pattern is obvious before you even get to the numbers. Sensor 1's row changes on every single line. Step 1. G is 1. Effective rate near the full learning rate. Step 10. G is 10. Effective rate already down to about a third. Step 50. G is 50. Effective rate down further still. By step 100, G has climbed to 100, and the effective rate has shrunk to a tenth of where it started. Exactly the 1/square root of tick curve from block 6, printed out row by row instead of just claimed. Sensor 2's row, meanwhile, does nothing for 99 straight rows. G sits at 0, but that is not why theta stays put. The gradient is 0 too, so rate times 0 is 0 regardless of what the rate reads. The parameter is not eroding while it waits. It is simply untouched. Then row 100. Sensor 2 finally fires, gradient 3, and that gradient is what sets G, jumping from 0 to 9, 3 squared, before any division happens. Because the firing gradient itself sits inside that square root, the effective rate lands near 1/3, and multiplying by the gradient of 3 gives the printed update, exactly 1, a full eta-sized step landing on the very first real event, the same number the handproof gave us in block 7, now generated straight out of running code. Now stretch time much further than 100 steps. The loop from block 8 would take forever to run out that far, so swap it for the closed form shortcut. For a parameter that fires every step, effective rate is just 1 over the square root of t. Print that formula at t equals 1, 100, 10,000, a million, and the output tells the whole story without running a single extra step. 1 a tenth, 100th, 1,000th, shrinking every time, never climbing back up. Packed snow does not spontaneously turn back into fresh powder. Here is the failure named precisely. G only ever grows, so the effective step size only ever shrinks, for every parameter that has ever fired, forever. Early on, that is exactly the right behavior, but real training runs are long. The ground beneath every parameter keeps shifting as the whole model updates around it. A direction that did not matter at step 1000 might be exactly what is needed at step 100,000, but by then, the terrain has already frozen solid there. G has no way to forget. Eventually, the step size drops below the size needed to move anything at all. Training does not stall because it converged. It stalls because the ground ran out of give before the model finished the journey. Momentum fixed direction, but left every parameter sharing one step size. AdaGrad gives every parameter its own step, earned from its own history. The rare critical signal finally gets the response it deserves, but the ground only ever hardens, never softens. That is the same mechanism, cutting both ways. What if the ground could partially thaw? Replace that ever-growing sum with a moving average, and old history starts to fade as new history arrives. Same idea, divide by the accumulated activity, but this time, forgetting is allowed. That is RMSProp.